Hello everyone. Today we are going to discuss about the topic voltage control method. Okay, so voltage control method we are going to discuss. So there are the two types of speed control variation in voltage control. One is the multiple voltage control, another one is the ward linear system of speed control. Okay, so we'll talk about the multiple voltage control system. So here the shunt motor. Okay, so it will be applied for the shunt motor. The shunt motor shunt field winding connected to the permanent fixed exciting voltage. Okay, so in this type of voltage system we are connected to the fixed exciting system, the field winding of the shunt motor. Okay, so in this the armature supplied the different voltages by the suitable switchgear. So what we are going to do here, we are applying the fixed excitation and the armature is supplied with the different voltage by suitable switchgear. And here the speed of the shunt motor is by applying the different voltage to the armature. That is, here we are going the this method we are using the rarely. Okay, so if we go that, so this is the in this method. So what we are doing, so here we are having the field winding. Okay, so this is the field winding, here is the armature of the shunt field. So here what we are doing, so we are the shunt field is excited by the permanent AC source. Okay, separated, and the armature. Okay, so armature is separated by the another voltage source. Okay, the speed of the shunt motor is applying the different voltage level to the armature the for voltage control method. Okay, so here another type is, that is wall layouts of speed control. Okay, here we can see the shunt motor. Okay, so we are having the permanent generator. Okay, so motor generators we can apply, and generator field we can see that. Okay, so the shunt field, okay, supplied is there, and prime mover of the DC shunt motor, and speed is control. Okay, so here the we are having the prime mover that is run by the generator. Okay, and motor is there. Okay, so here, so this system eliminates the disadvantage and flux control and armature control method. So what we are doing, selling that, so this war linear system eliminates the disadvantages of flux control and armature control method. So here we'll talk about the disadvantage of flux control. So that is a higher speeds. So higher speed, double speed we can get. So but at the, if I go for higher speeds, what will happen, it's suddenly stable. And if it goes to the talk about to the armature control method, in armature control method what happens, so while apply the load by using the armature speed control method, what will happen, so it will be affected on the speed. Okay, so by applying the load the speed control method by using armature control, so it will affect the output and efficiency. So we can reduce these advantages by using the ward linear system. Okay, so here the speed of the main motor. Okay, so here we are doing the speed of the main motor is controlled by varying the input voltage to the main motor. Okay, so that is we are doing the motor. Okay, so what we are doing, so here is the motor is there. Okay, that is run with the generator. Okay, that is run with the generator. Okay, the speed of the main motor is controlled by the varying the input voltage of the main motor supplied by the DC generator. Okay, so and DC generator mechanical input is given by the prime mover of a DC or AC motor. Here to run the DC generator, so we are connected to the one prime mover, either AC or DC motor. Okay, so here the generator output can be varied from 0 to its rated value by varying its field current through the potential divider. Okay, so here we can see that here we are having the field winding, and here is the this is the motor field winding for speed control, and this one is the, okay, so this is the motor speed. Okay, so the prime mover. Okay, so this is the main motor which are going to control, so that shunt field winding. Okay, so that is varied. So here the prime mover. Okay, so it is the both are connected. Okay, so that is power supply is connected to the motor. Here one thing remember we have to do so motor generator. Okay, so prime mover and gen, so it may be AC motor or it may be DC motor. Okay, so both are running that, so mg set, and the power is supplied to the motor by the DC generator. Okay, shunt field of the motor is connected to the here output of the generator. Okay, so here the field of the main motor is connected permanently to the DC supply, that is the DC generator, by reversing the direction of the generator field. Okay, so by reversing the direction of generator field, current means of the potential divider, the speed of the motor can be varied from its maximum rated value in one direction to the maximum value of the reverse direction. Okay, that is we are varying the speed of the motor by varying the field. Okay, reversing direction of the generator field current by means of potential divider, the speed of the motor can be varied. So for controlling a DC motor we are varying the generator exciter. Okay, so generator field current we are varying. Okay, so n rated to n rated. Okay, so here are the advantages. So no armature series resistance loss and no instability in the motor speed because we are exciting with the DC generator. Okay, so there is no directly connect to the armature, right? That's why here is no resistance. Next, wide range of speeds and its variations is smooth. Okay, these are the most advantage. And quick speed of the motor can be reduced quickly by reducing the field of the generator. Okay, so the speed of the motor, okay, is by varying by the supply. So by supply is getting from the DC generator, so that generator will be ISP, we can reduce. And there is the unlimited speed control in either direction of the rotation. Okay, that is we can go to the forward direction, reverse direction. Okay, that will be varied. So here in the disadvantage, that is we have to place the another mg set. Okay, that is the most expensive and lower overall efficiency. Okay, so if you run this at light load condition we will getting the low overall efficiency. Okay, if we run for higher loads it will be more applicable. Okay, so applications, so we are using the winders and elevators, coilary winders and elevators we are using. Okay, so here if we talk about the another topic, that is speed control of the DC series. Okay, so in the previous we are talk about the shunt, so we'll talk about now discuss about the speed control of the DC series motor. So in the DC series motors widely used in many applications. So that is the first main thing is that is the electric traction. Okay, and cranes and hoist and trolley cars, conveyors, rapid transit system. Okay, these are because it's the traction. Okay, so the torque power. Okay, so initial and running torque is high for the DC series. So that's why we are mainly using the heavy load conditions, right? So that's why the applications are very wide compared to the DC shunt. Okay, so electric locomotives we are, so there are the three main methods of the speed control of the DC series motor. One is the voltage control, and is the armature control, and flux control or field control. Okay, so voltage control, armature control method and flux control methods of these will having the similarly in the DC shunt also. Okay, so this is the voltage control method, that is in series we are placing the series and parallel method. Okay, so here we are placing, okay, so armature, so the series field are connected to the another motor. Okay, series field. So here what we are doing, the voltage across identical DC series motor of 2 or more. Okay, so what we are doing, voltage across the identical DC series motor of 2 or more by connected them in series or parallel or series parallel combination. If it is connected in series, one condition. Okay, so if connect the two in series or multiple, that is okay. So series or parallel combination we can connect. So let flux per pole is a 5. Okay, the back EMF and speed of the motor combination is n1. Okay, so n1 is directly proportional to the EB by 5. Okay, as we know, so by, so from that we can get, that is EB Okay, so back EMF, that is V by 2. Okay, because the voltage across that will be varied. Okay, so we can see, so here V1 V2, right? So voltage is dividing the both sides, so V2 by 2. Okay, so V1 by V2. Okay, that's we are right. V by 2 IA of RA plus RSC. Okay, so from that we'll getting the V by 2. Okay, of I. So that is we are taking, that is okay. So here the voltage, okay, so drop is very small. So here, if you go for the parallel connection, okay, so here the by combining the two series identical machines in parallel, we are maintaining that. Okay, so in this time, the flux per pole is back EMF speed can be N2. Okay, at this time, so we are getting the equations, that is 2V by N directly proportional to V by IA. Okay, so here we getting the two equations, that is first series connection and parallel connection. Okay, we are getting the, that is I. Okay, 4. So here that is therefore N2 is equal to 4 N1. Okay, so thus in parallel connection 4 times the speed as compared to series connection can be obtained. That is series connection. Okay, in the parallel connection 4 times the speed as compared to the series connection. So we can get more speed controlled by connecting the parallel connection compared to the series. Okay, so here is the advantages of the series and parallel connection. So different speeds by connecting series parallel connections in electric traction, okay, using in high starting torque cranes and tractors, so that will be more applicable. Now we'll talk about the armature control method. So here armature control method, just we are placing the rheostat in series with the series field winding of the motor. Okay, by varying these rheostat we are controlling the armature current. Okay, from that we can control the speed of the motor. Here variable rheostat placed in series with the armature. So here when is directly proportional. Okay, so it is N is directly proportional to the EB. Okay, so from that EB is equal to V minus IA of RA plus RSC. Okay, so here is the additional resistance also we can place plus R. Okay, so here higher the value resistance, higher voltage drop and lesser the EMF, hence lesser the speed. Okay, so that means whatever the drop is there, if you are increasing the speed also we can decrease. So lesser the variable resistance, lesser the voltage drop, high EMF and higher the speed. So we are placing the resistor in the very less, so we are getting the higher speed. Okay, speeds below rated values can be obtained. So in this method we are using the armature, so below rated method. So this is the parallel combination, that is the flux control method. Okay, so in the flux control method we are placing the parallel to the field winding. So in the shunt field winding we are placing the in series, but here we are placing the parallel. Okay, so N is equal N directly proportional to EB by 5. So change the flux of changes the speed of the DC motor. Okay, so by this method is a field diverter. Okay, by connect the, so here variable R resistors connect across the field winding. As part of load current flows through the variable resistance, and at the constant load this makes series field winding current reduces, so reducing the flux. So what we are doing, so we are applying by bearing the field restart, okay, by means of the external resistor, so that the flux is controlling. So reduction flux increase the speed of the, so this will be applicable for the above rated speed. So these are the method we can see. Okay, so here armature diverter method. So that is a, if it place in the, if placing the series field with the parallel, that is the field diverter. So if you are placing the armature in parallelly, so that is the armature diverter method. Okay, that's two. So in the field gravity. So this is for the arboreted we can get. Okay, so if variable resistors connect across the armature we can see. So a constant load, additional current id, okay, that current is flows to the id, v minus ia ra by we can get through the series field. So here we can another method. So we by using the uh, tappings. Okay, so reduction. So additional current makes the field flux, hence reduction in speed. So speed can be rated by became obtained. Okay, this is the tapped field control. Okay, so in the tapped field control method, so number of turns of field winding can be varied, thus changing the flux and resulting in change of speed. So that is here. So by varying this, so by varying this field rheostat, okay, tapping, so we are placing the this one, so this will be placing by means of the tapping. So by varying this tapping we are increasing the speed or decreasing the speed. Okay, so number of turns of the field can be varied, thus changing the flux, so resulting in the change of speed. So by varying the field turns, so we'll getting the change of speed. So when one or more turns are shorted, the effective ampere turns will be reducing, providing the less flux. So reduction flux increasing the speed. So speeds upward from the tapped. So however, increasing the number of turns, more number of turns required to the speed. So any speed can be obtained. So rated speed, above rated speed we can obtain from this method. So that is the rated value of speed and below rated. Okay, so above rated also we can get. So these are the speed control methods of this DC shunt and series